Okay, welcome everybody. Happy New Year and welcome back to the first CMFI Mass Spec meeting this year. It's my great pleasure to have now brand new Professor Wout Bittremieux giving the seminar today on machine learning applications for proteomics. So to give you a very brief intro, Wout is a computer scientist. He did his PhD at the University of Antwerp, already in the field of proteomics, so a long-term expert. He then did a postdoc in Seattle at the University of Washington, and then also at the University of California in San Diego, where I was fortunate to spend some time next to him in the office. And now recently he moved back to Antwerp to start his own group there. Yeah, as I already said, he's I think excellent expert in the field of computational proteomics. Now also a little bit metabolomics, but yeah, I think a long-standing track record there with multiple workshops and short courses at ASMS and stuff. So I think it's really amazing, and it's super awesome to have him here today. So very much looking forward to your seminar.
Thanks, Daniel. And yeah, it's true. We literally had desks next to each other in San Diego. So it's a pleasure to be here and give a seminar on machine learning for mass spec. So to the extent possible on a Zoom lecture, I would like this to be a little bit interactive. So if you have any questions, put them in the chat, use the Zoom functionality to raise your hand, and I'll try to monitor that as I'm going to address those questions. Machine learning is huge. There are lots of algorithms, lots of tools that you can use. So in the short time that we have, unfortunately, it's not possible to go over everything. So I'm mainly going to focus today on a little bit of some high-level concepts in machine learning that might help you and that might assist you in how to interpret machine learning in the scientific literature, because nowadays there's hardly any paper that you read in journals that doesn't use some kind of machine learning, and with the massive amounts of data that are being produced, having some data science skills, some machine learning skills is just, I think, an essential skill set to have as a scientist. So what we're going to discuss today is I'm going to describe what machine learning is and why it's useful. I'm going to talk to you about two different ways of machine learning called supervised learning and unsupervised learning, and what the difference is between those two of them. I'm also going to explain the difference between regression and classification tasks, explain a little bit of detail how a machine learning model, how that model building process evolves, and I'm really going to emphasize the difference between training data and held out data to evaluate your models, and brief introduction to the bias variance trade-off and how it relates to overfitting. So what is machine learning? Well, in traditional programming, of course, we have a computer, you have some data, you have rules, expert information about your data, and you encode these rules in your computer, you apply these rules then to the data that you have, and that gives you a certain set of answers. So, for example, you want to build a heart disease predictor. You have some data with different information about patients, BMI, their history, and so on. You have a certain rule, you know, if BMI is above 25, higher rate of, you know that there's a higher rate of heart disease. So you encode this rule: if higher than 25, heart disease is likely. So that's a traditional way of programming where you have these rules based on expert knowledge that you explicitly encode. Now, in machine learning, this paradigm is flipped around a little bit. You still have your computer, you still have your data, but now rather than rules, you have the answer. And so you provide the computer the data and the answers, and you let the computer figure out the rules by itself. So now rather than knowing this rule that if your BMI is high, is a larger, more significant rate of heart disease, now you have data about BMI and you have answers linked for those patients, and you let the computer figure out themselves what the relationship between BMI and heart disease might be. So this is kind of a different paradigm that is used in machine learning. And then, of course, once you have used a machine learning algorithm to derive these rules, you could also then use the rules in a more traditional setting and use those rules to make predictions for new observations, where you have the data for new observations. The rules were learned from your previous data, and you use that to then come up with answers for your new data. And so this traditional programming versus machine learning, you can kind of compare it to cooking. In traditional cooking, you have a recipe, all of your ingredients on the one hand, you have the recipe with different steps, you apply that recipe to the ingredients, and in the end, you have a delicious meal. Machine learning then is you have as input your ingredients again, and as output you have the end result, which is something that you might see nowadays on all of those recipe blogs. You know, they start with a photo, an Instagram-worthy photo to make you exciting about the meal you want to cook, and then there's like a list of ingredients, and then there seems to always be like a kind of a long, winding personal story about how their grandma used to cook it and how they ate it and all these emotional attachments. And it's only until you scroll way down to the end that you find the actual recipe. So it might as well not be there. So this is a little bit, if you go to one of those cooking blogs and you check only the glamour photo and the ingredients, and then you try to figure out yourselves how to make this recipe. In Spec, one of the examples that or in proteomics, one of the examples where you could use machine learning is we can predict the peptide retention time from your liquid chromatography based on its hydrophobicity values. So the Gravy score is a measure of hydrophobicity. If we have that as input, can we use that to predict the retention time of the peptides? So we have data on the one hand, Gravy scores for a few peptides, and answers, the retention time for those same peptides. And we can plot it here, Gravy score and the retention time, and against the retention time. And from this plot, you could already discern that, yes, indeed, there is a relationship between the Gravy score and the retention time. We can probably find a model that converts the Gravy score into retention time. So that's what we want to find. This model, these rules, that's what we want to find with machine learning. So the rules, and kind of in machine learning speech, this is a function that maps a peptide's Gravy score to its retention time. And it would very likely be something like this, a linear function that maps from Gravy score to peptide retention time. And that's what, this here this would be a linear function, but there are lots of different machine learning algorithms that we could use to find this function. And that's kind of the whole process that machine learning is about, going from data and answers to the rules that link those two together. So the challenging aspect then is to find this function that generated the observed data. I have a few mathematical notations in the next few slides, because that's how often machine learning models are described. But I'll explain how these work, so you don't need to be too intimidated by them. Here, f is the function that we want to estimate. And this function maps one or more input variables to one or more output variables. So input variables are x, and it maps it to our output variables y. A few examples of such a function could be predicting disease status from a panel of biomarker abundances. In that case, the biomarker abundances are the input variables, and the disease status is the output variable. Or defining disease subtypes from analyte profiles. The analyte profiles are the input variables, disease subtype is the output variables. Predicting the retention times of peptides from the peptide sequence, similar to our previous example from the gravy score, but now you could also envision doing it from the peptide sequence, so the individual amino acids directly. And there are lots more examples where we could use machine learning. And so machine learning then describes the process of finding the best approximation of this function f, which is also typically called the model from the input data. And this input data that we use to create the model is typically used called the training data or the training set. So the model is trained on our input data to predict our output variables. So like I mentioned, our function f and then here x are our input variables, or also often called features. And the model learns from these features. So features can come in lots of different shapes and sizes. You can have tabular data, which could be here an abundance matrix, something that we work with quite often, where we have samples on the rows, different analytes on the columns, and then some kind of abundance values in the cells. Can also be images, mass spec imaging data, or just any kind of image data for non-mass spec related machine learning. And sequences. Peptides are sequences of amino acids. Small molecules can be represented as smile strings, which are also sequences over specific alphabet. And even mass spectra themselves can be considered as sequences of different fragment ions that are represented by tuples of their MZ values and their intensity values. And based on what kind of data you have, we'll typically use different kind of models. And some models are better for some type of data, and other models are better for other types of data. But there's really a lot of different data modalities that can be processed using modern machine learning algorithms. One type of machine learning is supervised learning. And supervised learning uses known outputs for our examples. So the output variable here is y. In supervised learning, the output variables are labels that are known for the model, for each example, to learn a model that can predict the same set of labels for new data. And labels can be either continuous, such as retention time, which is a continuous variable between 0 and the duration of your experiment. And in that case, we're talking about a regression task, or they can be categorical. So charge state 1, 2, 3, 4. so only a limited number of categorical features can also be healthy or diseased, 0 or 1, which also categorical features. And in that case, we're talking about a classification task. Supervised learning is the most common application of machine learning that you'll find. However, sometimes we might not have labels for our training data. And this doesn't mean, luckily, that we can't use machine learning at all. We can still model the relationships between examples in the training data. For example, you can find clusters of related examples. Spectral clustering, you don't have cluster memberships in advance, but you can still, based on spectral similarity, find clusters of related examples. In that case, our output variable, y, will be the cluster assignment for each example that you then learn from the data. Or you can reduce high-dimensional data to a low-dimensional space that captures some of their latent characteristics, such as using PCA, PQA, other dimensionality reduction techniques. In this case, our output variable, y, are the low-dimensional coordinates of the data, or also often in machine learning called embeddings. And all of these are unsupervised learning tasks. So the difference between supervised learning and unsupervised learning is, in supervised learning, we have labels already provided as input for the model, whereas in unsupervised learning, labels are unknown in advance, and we kind of find patterns in the data that we then use to predict the output variables. And so there are lots of different, even that's supervised versus unsupervised, but there are lots of different applications within each of these categories as well. So this is a little flowchart to kind of help decide what kind of machine learning task is relevant in specific situations. So the first question to ask yourself is, do we know the output variable y? If we don't, we're talking about unsupervised learning. We're learning labels from the data directly based on patterns in the data, such as spectrum clustering, embedding spectra in a low-dimensional space, image segmentation, finding specific parts of the image that are most relevant, or metabolite structure recommendation, and other examples. If you do have labels, then we're talking about supervised learning. And then there's a second subdivision based on whether your labels y are continuous or categorical. If they're continuous, it's a regression task, such as retention time prediction, collisional cross-section prediction, fragment ion intensity prediction, and so on. If the labels are categorical, we're talking about classification tasks, such as biomarker discovery, analyte observability, peptide spectrum match rescoring, and so on. Now, one saying that you might have encountered before is all models are wrong, but some are useful. Now, what this means is that the real world is so complex that even the most advanced machine learning model is not going to be able to model everything perfectly. Or you would need to have like an Oracle computer that uses quantum simulations to simulate everything starting from the Big Bang up to now. Then maybe that is the one model that violates the saying. But other than that, all models to some extent will never be able to 100% capture the real world. However, that doesn't mean that machine learning is just a fool's errand. There are still lots of models that can be useful. But to capture some of this uncertainty that we observe in the real world, usually machine learning models also have kind of an error term in there. So we have our function, we have the input variables, output variables. In addition, there's a random error denoted by the Greek epsilon here. Because real data always contains variability that cannot be predicted. And sometimes it's also much more benign errors or variability than just complexity of the world, but there can also be measurement error in the features or labels. Someone might have made a mistake in data entry, or just the fact that mass spectra are some kind of stochastic measurement of the abundance of a certain analyte in the instrument that is at a certain time. There can be unmeasured features that affect the data. If your input features X are incomplete and they don't contain all of the information that is needed to come up with the rules, of course your model is not going to be able to capture that information if it hasn't been provided as information. So unmeasured features can kind of blind spots can have a large effect on the performance of your machine learning models. So keep in mind that no machine learning model will be perfect, and if a model is perfect, you should be very, very skeptical, because I trust a model that has non-perfect performance much more than something that gets 100% accuracy and so on, because that indicates that there might be some issues with the data or how you're phrasing your prediction task. So, okay, we've now had kind of a large helicopter view of how we use machine learning to go from input variables to output variables, and how, and we do that using a function f. But how do we actually come up with this function f? Well, we use basically a lot of mathematical and statistical techniques to approximate this function f from our data. And the model building process goes a little bit like that. First, explore your data. And this is maybe, I want to take a second to really emphasize this, that this is the first step. And often when you read papers, the papers immediately, the method section go, we have this data and we did this and this and this and this for modeling. And it kind of completely skips over the first step, which is data exploration. But nevertheless, all of the researchers did or should have done this step. And it's like extensively exploring your data. Understand what information is available in your data, because without that, you're never going to be able to properly build a model. So exploring your data, looking at the raw data itself, visualizing some of the data, and so on, I think is essential for any successful application of machine learning. Next, based on now your knowledge of the data, choose the features for your data. Come up with features that can describe the rules that you want to learn from your data. This is, in machine learning, it's often called also feature engineering. And these two steps, like I said, even though they're very rarely described in detail, people usually, a rule of thumb is that these two steps take up 80% of the time, and the actual model building only takes up 20% of the time. Whereas if you go to the scientific literature and read descriptions or read blogs on the internet about machine learning, 80 to 90% of the time is about the actual model building, and people gloss over the data exploration and feature engineering. But these are kind of maybe even the most essential steps during the model building process. Now, after you know how to transform your data into features, then you can pick a machine learning method that aligns with your task. And what this means is, if you have an unsupervised clustering task, you're going to use a clustering algorithm. If you have a classification task, you're going to a supervised classification task, you're going to use a classification method. And within all of these different categories that we saw just a few minutes ago, there's still lots of different algorithms that you can use that each have their own strengths and weaknesses, where you could still fine-tune which machine learning method to use. But in the broadest terms, this is these different machine learning tasks that you need to go through and figure out which kind of methods is relevant for your task. And then the actual training process is you then use that machine learning method to fit the model to your training data. So based on the training data, the input variables and the output variables, you fit the machine learning model to learn the rules. And this is a broad overview of the model building process. And we'll go a little bit deeper into this fitting process. And even though I just mentioned that this is actually only 20% of the time, rather than discussing all of the data exploration and feature engineering, we are going to talk about the model fitting step a little bit more now, because data exploration and feature engineering is a little bit more challenging to talk about in general terms, because it is highly application specific. It depends on expert knowledge, whereas fitting a model is a little bit more general. And even though we have all of these different algorithms, they kind of all at a high level work similarly. And so fitting a model or learning or training a model, these are terms that are used interchangeably, refers to finding the parameters of a model that best fits the training data. And this might sound a little bit vague, and that's because best fit, what that means, it kind of depends on the method, on the task you're trying to solve. But for example, in linear regression is kind of a little bit more the machine learning term. Ordinary least squares, or OLS, is a little bit more the statistical term, but they are the same thing, used by two different but related communities. Linear regression you can write down like this. You have your output variable y, you have your input variables x1 to xp, and you want to learn the parameters of your linear model beta 0 to beta p that best fit the data. So again, x are the features, y is the label, and then you learn your parameters beta. Or you can also write it in matrix form, and here then y is an n/1 vector for n samples, one output label. X is an n/k vector, n samples, k features, and then beta is a k/1 a matrix, and then beta is a k/1 vector. And you can also write it in matrix form, and that's often how it's done to solve these equations efficiently. And then OLS, what it does, how do you then define the best fit? What are the optimal parameters? Well, the parameters that minimize the mean squared error. That is the optimization function. That is the function that OLS optimizes, mean squared error, or MSE, indicated by the L for loss that you'll often also encounter. So mean square error is computed by taking the difference of your label for each sample and the predicted y, and the predicted label for each sample y hat, squaring the difference, summing it over all samples and dividing by n, so to take the mean. So it's literally, as the name says, the error, you square it, and you take the mean. And the parameters that give you the lowest mean square error are the ones that you want to find. And that's the solution for a linear regression algorithm. And if we exemplify this with our peptide retention time example, we have a gravy score used as input to predict the retention time. How we do this? Well, first we calculate the errors or the residuals. So those are the deviations from our samples, between our samples and the linear regression, the line that we found with linear regression. So here the yellow lines indicate the error from what our model would predict. So these are the errors. We square those errors, and then we average the squared errors, and that would give us the mean squared error for this specific data set and this specific model. Now let's assume that rather than the linear decision function that we had previously, that we here, instead of the linear regression, now we have a magical mystical model called the squiggle. And the squiggle has also, we provided it our data, we told it to find the best fit, and this is what the squiggle model came up with. Similarly for the squiggle model, same as for the linear regression, we can compute the mean squared error. Again, we calculate the errors or the residuals, again in dark yellow, square those, and average them out. Now the mean squared error for linear regression on this data set was 49 minutes squared. The mean squared error of the squiggle model was 5.62 minutes squared. So just based on those values, you might say, okay, the mean squared error for squiggle is much lower than for linear regression. So squiggle is the model we want. We're gonna use that one. However, this might not necessarily be the full truth, because the next step after fitting our data, our model to the training data, the next step in our model building process is to then assess how well the model performs, and that's what we did with our mean squared error. But rather than evaluate the model on training data, it is paramount to always evaluate your models on new data. And so here again, we have our two models, linear regression and squiggle, and we plot the linear regression, the mean squared error of both models. And the squiggle model fits the training data really well. We get a higher mean squared error for the linear regression and the squiggle than the squiggle. But if we have some new data points coming from the same distribution that were not used during training, called our validation data or test data, and we apply both of those models, now we actually see that our linear regression kind of performs rather similar for the new data than it did for the training data. Whereas the squiggle model all of a sudden performs much worse for these new data than for the training data. So turns out that although our squiggle model initially seemed very promising, if we have new data that comes from the same data distribution, all of a sudden it doesn't perform well at all anymore. And we actually say that the squiggle model is overfit to the training data. So this demonstrates why your model evaluation stage is super essential, and why you have to do this on new data that was not used for training, to get like an unbiased assessment of model performance. Because you don't want to train a model that works perfectly for training data, but doesn't work at all for any new data, because then your model, you can't use it. You want a model that also works as well on new data as it does on training data, so that you can use it for future newly acquired data afterwards as well. And so that kind of brings us to the prime directive of machine learning, and that is to only evaluate your models on data that has never been used for training. And I'm going to repeat this again, because this is the most essential takeaway. If you remember anything from this hour, this is the most essential takeaway. Only ever evaluate your models on data that has never been used for training. So don't cheat. Don't think, oh, I can train a model, see what works, and then split into train and test, and then, I'll still be fine. No. The first step you have to do in any machine learning task is, before you start doing anything, split it into training and test. Don't touch your test data until you're writing up your paper. And then only you evaluate your final model on your test data. Because otherwise you're just fooling yourself, and your models will be useless. So yeah, split your data into training and test before even exploring it, and then only use the test set at the very end to evaluate your model. If you want to evaluate your model sooner, of course that's possible. Don't use the test set for intermediate evaluations though. Split the training data into a second subset, in training and validation data, and then use the validation data to iterate on your model. For example, to tune hyperparameters. Hyperparameters are options for your machine learning model that are not learned from the training data. So in that case, you use a validation set to do this iterative model refinement. And then after you have trained the optimal model on your training data by evaluating out on the validation set, all the way at the end of your modeling tasks, only then use a test set to evaluate your machine learning model only once at the very end of your project on the test set. So our model building process is actually gets an extra step then all the way at the beginning, which is split your training data. And then the whole model building workflow is performed on the training data only. Your test data has been split off initially. You don't touch it at all during this model building process. You only use your training data during those tasks. And then only at the very end, use your tests split to evaluate your model. And this is relevant because you want to get an objective assessment of your model performance, and held out data helps you to reveal the bias variance trade-off. And bias and variance are two terms that are often used to describe the performance of machine learning models. And for example, in flexible methods, like linear models that we've used in the example before, assume a strict functional form for your function f. A linear line or a linear hyperplane is a very restricted form that your model can take. If this assumption is wrong, so if your data cannot be separated by a linear line, we say that the method has a high bias. On the other hand, flexible methods can model virtually any functional form of the function f. So for example, deep neural networks can learn any kind of nonlinear decision function. However, without enough data, this flexibility will result in overfitting. So your very flexible model will perfectly learn the training data, but then if you have new data that has never been seen before, the results will be incorrect, and because that's overfit on training data. We call this a high variance, and variance describes how much a method changes when given different data generated from the same underlying process. And so can kind of there is always a little bit of a trade-off between bias and variance in terms of model flexibility. So we have here on the x-axis model flexibility. On the left, we have very inflexible methods like linear models. On the right, we have very flexible models like deep neural networks. If you would then evaluate your model on a test set, so not on a training set, but on a test set, you will often see that there's kind of a sweet spot in the middle between very inflexible and very flexible methods. Because if the methods are very inflexible, they will have high bias. As mentioned before, they can't model the data accurately, whereas very flexible models have extremely low bias because they can perfectly fit the training data. However, in that case, you're also overfitting to the training data. And if there is new data that is slightly different than the training data, actually make a lot of mistakes. So this indicates that you have a very high variance. Whereas the inflexible methods, they generally will not have a high variance, but instead a low variance. So you want to find the optimal spot in this bias variance trade-off. You want to find the model with just the right flexibility that trades off bias and variance, and then minimizes your error on unseen new data. And so you can have different kind of models and models with different kinds of bias and variance. You can have models with high bias and low variance. So you want a prediction here in the middle of your target. If the predictions are off, but they're always off in kind of the same way, your model has high bias and low variance. If the predictions are kind of in the right location, but there's a lot of variability, your model has low bias and high variance. Of course, the worst situation is when you have high bias and high variance. So your predictions are way off, but they're also highly variable. And the optimal model that we all aspire to is the one that has low bias and low variance, so that your predictions are correct and there is not a lot of variability between performance on the training data and the performance on unseen new test data. And so this then closes the loop on the model building process, where after assessing how the model performs and evaluating the bias and variance trade-off, you can then use that to iteratively refine your model and try to find your optimal model that finds the sweet spot between bias and variance. And ultimately, after going through this process a few times, you have come up with the model you're satisfied with, and only then you're going back to your test set to evaluate how well the model does on new unseen data. So there's a lot of information about how machine learning works and some general aspects thereof. So let me give a quick recap. of what we've discussed so far. So machine learning tries to learn a function that goes from input data and input features to the provided output, the labels. Input data consists of examples described by features, and supervised learning methods map these features to known outputs or labels. If the labels are continuous, it's a regression task. If the labels are categorical, it's a classification task. In unsupervised learning, we don't have labels, but instead these methods, these algorithms summarize relationships between examples. Machine learning methods are trained by optimizing the parameters of a model to best fit the training data, and then split your data early and often. Only evaluate models on held out data, your test data set. During the model refinement, evaluate them on validation data that has been split off as well. Inflexible models may have a high bias, but are good for small data sets because there aren't a lot of features. There aren't a lot of examples. It's easier to overfit to the few examples that you have. So if you don't have a lot of data, you might want to prefer models that have a high bias. Flexible models may have a high variance, but can be tamed with a lot of data. If you have hundreds of thousands to millions of examples, like some data sets have nowadays, the risk of overfitting is lower because it is almost impossible for models to memorize that many examples. So that's kind of the winning combination, where you have lots and lots of data, and then you can use very flexible models to get optimal performance. And I'm now gonna end with an example, specific use case of machine learning in proteomics, and that is using machine learning for de novo peptide sequencing. So de novo peptide sequencing, typically the standard approach for spectrum identification is using sequence database searching, where you have your experimental spectra and you have a sequence database. You convert your sequence database, you do in silico digestion, you convert them to peptides, and then you match the experimental spectra to the theoretical peptides and find the ones which give you the highest match score. So that is based on, you have your reference proteome, and you only look for those peptides that are part of your reference proteome. In de novo peptide sequencing, however, we don't work with a reference proteome. Instead, we try to derive the peptides from the spectra directly. And how we do this is, you can, between the different peaks, there are going to be gaps, mass differences, and if this specific mass difference corresponds to the mass of an amino acid, we say that, okay, that's probably that amino acid here, another amino acid here, and so on. So here, for example, for this spectrum, we can use de novo sequencing to interpret it as the following peptide, because all of these mass differences between the peaks correspond to these amino acids. So this is the mass difference of arginine, and so on. And based on all of these mass differences, we were able to directly come up with a peptide label, a peptide sequence in a de novo fashion. So that's how de novo peptide sequencing works. And the way I explained it, just by looking at the mass differences between subsequent peaks, that's kind of how this was done decades ago by hand, where people were printing out mass spectra and using a ruler and carefully checking the mass differences between subsequent peaks. And this is kind of the same process that traditional de novo algorithms performed, except that it was just encoded in a computer. the algorithms were just checking the mass difference between peaks and trying to figure out whether those fit specific amino acids and trying to come up with a peptide sequence that way. However, now in recent years, we're seeing more and more machine learning methods that that are used for de novo peptide sequencing, and especially notably, like recently, deep learning is starting to be used to solve the de novo peptide sequencing problem. You can kind of compare this to a sequence-to-sequence prediction task. And where a lot of these machine learning tools are developed is in neural machine translation. So you have an English sentence and you want to translate this to German. Well, the input here is a sequence of words, so words of variable lengths, and the output sequence is also the output is also a sequence of variable lengths. I'm not going to try to pronounce this because my German isn't that great, but you know, the length of the input sequence might not necessarily be the same as the length of the output sequence. English and German are pretty similar, so word order is kind of consistent, but in other languages it might be completely different. So this is actually a pretty challenging task, and there are a lot of investments in trying to solve this. And what most state-of-the-art tools do is they kind of use an encoder-decoder architecture, where the encoder takes your input sequence, it's one by one, so it takes first mass, then spectrometry, then then really, then awesome, and it builds up an internal representation by processing the input sequence token by token, and then from this internal representation, a decoder is used to then again token by token provide an output that is the German translation of your input sentence. And we can kind of do the same thing for mass spectra and peptides, because actually both of those are also can be represented as sequences. So this is again a sequence-to-sequence translation problem. Your MS spectrum can be represented as a sequence of fragment ions, where each fragment ion is represented by its M over Z and its intensities. This is input in the model through the encoder block, and then the output is also a sequence of amino acids. So we have here the internal representation, and then the decoder kind of predicts which peptide this initial input spectrum corresponds to. So this is kind of a application of sequence-to-sequence translation that was developed for neural machine translation that we just very recently, we released a preprint last week. We applied it to mass spectra and de novo peptide sequencing. And if you look at the performance, here in green is a traditional de novo peptide sequencing algorithm. In orange is kind of a first generation neural network de novo algorithm. And then in blue are two versions of the new tool that we just released. And especially here, light blue is the best version. And you can see where we want to be here in this plot is here, the upper right corner. Because the peptide precision is how many peptides, how many spectra are correctly predicted with their peptide, and then the coverage is how much of the data set is considered when ranking the predictions by score. If you're here in the upper right corner, your full data set is predicted and all of the predictions are 100% accurate. So for our data set, we're about 80% of spectra. We can figure out which peptides the spectra correspond to. Whereas if you look at more traditional tools that are not really based on machine learning, but just like this expert knowledge, these heuristics, they only get 40% they can only figure out which peptide corresponds to 40% of the spectra. So this is a massive increase, and it indicates the power of machine learning for lots of different tasks, actually. This is one specific example. And I think machine learning is going to become pervasive in a lot of different things that we do. So this was just a very brief overview. If you want to read more, the preprint is available on bioRxiv. And so this is the final slide. Don't have a lot of time today, so I want to leave you with a few resources that you can use if you want to go deeper into machine learning. Especially the first one is an excellent book to learn about foundations of machine learning, with also lots of good hands-on exercises and tasks in R. There are also, here's a link of the same exercises with solutions in Python rather than R if you're a little bit more well-versed in Python. Another good book is by Kuhn and Johnson, and an applied book with examples in Python here by Sebastian Raschka. And then also some more Python resources, because that's what I'm most familiar with. For example, Software Carpentry has some very good lessons to learn some data science skills. Scikit-learn is a super useful machine learning library in Python, and that's basically what everyone uses. So I can share these slides with Daniel, and he can send them around. And so there are links to all of these resources that you can consult if you want to learn more about machine learning. So I want to thank you all for your attention. And if there are questions or things that weren't 100% clear, now is we're almost coming up on the hour, but I'm happy to spend a little bit of time to answer questions.
All right, awesome. Big applause. Wout, this was a great introduction and a very exciting new tool you have. I think there will be time for discussion and questions, and I guess there are probably some. But before we move on, I'm going to stop recording, and I just want to say goodbye to the people watching this, and to also the people who are going to hop off now. So good seeing you all. Hope to see you next time.